Okay, and the purpose will be lost in case of watermarking if it is abolished or heavily tampered. The watermark which is embedded inside the cover object, if it is heavily tampered, the purpose will be lost. On the other hand, if the attacker knows the communication about the steganographic communication process, then the purpose is lost for steganography. If the communicating message is decrypted in case of encryption or cryptographic based encryption, the purpose of the whole process will be lost. Now, just a little bit introducing steganography, it means covered writing. Steganography simply takes one piece of information and hides it with another one, right? So, in history, there were many incidences people were used technographic communication. One such incident was during the Persian Wars. Okay, Herodotus, the king of the Persian, he used to tell one of his messenger, who saved his head and allowed to write some secret information or message in the saved, in the scalp of the head. Okay, it can be tattooed on the scalp, right? And it will be waited until the hair grew back, then he will start his journey. Finally, at the recipient end, once again the saved head, the head will be saved, okay, and it will be, the message will be revealed. This was the first, the initial use of steganography during the historical use. Now, this whole graphical abstract, I would say, for steganographic system is like this. We have a original image, and the left side image I am discussing, and we have some secret informations, and these two will be embedded. This information will be embedded in the image, leading to provide a camouflage image, which will be transformed through an open channel to the receiving end, and this receiving during this open channel transmission, there could be possible any number of stego attacks. Okay, and at the receiving end, the opposite of the embedding process will be followed, and it will be retrieved. The information will be retrieved. Okay, this is the steganographic system, or we may say irreversible steganographic system. Suppose at the receiving end, the receiver able to recover the original image as well as the secret information, then it is called as reversible information hiding or reversible, that is steganography, right? So when we discuss about steganography, is the classification of steganography, as I discussed, as I said, is very crucial. We have two kinds of steganography techniques, as I discussed. One is irreversible, other one is reversible. In case of irreversible techniques, there are some popular techniques like least significant bit, pixel value. Least significant bit is also in short called as LSB technique. Pixel value differencing in short called as PVD techniques. Combination of both of these LSB and PVD, we say LSB plus PVDs. And we have a modulus function technique, MF. And also we have a red, green, blue RGB steganography. And then we have a turtle cell based steganography. We have LSB array, LSBA, Sudoku based, and we have a combination of both PVD and modulus function, PVD plus modulus function steganography. It's not certain that they are all irreversible. Alternatively, we can use based upon our technique. Okay, how does it can be used whether for reversible or irreversible? But anyhow, in the literature, authors have provided these kind of state of art techniques. Okay, coming to reversible information, has image steganography techniques. One is difference expansion is very famous. We have prediction error expansion. We have histogram shifting. We have combination of histogram shifting and prediction error expansion. We have dual image based information hiding. We have interpolation based steganography, reversible one. So these are the classification of information image steganography techniques. Let us first try to understand on which parameters these image steganography techniques basically relies on. If you see the parameters, the three most important parameters are like one is output image quality, which is the stego image quality. This is something called your imperceptibility, okay, and the capacity. Capacity is nothing but the amount of information an image can embed. The robustness. Robustness is similar to your security. That means there is some attack during transmission, but how does the proposed embedding technique resist that attack? It's called as robustness. Okay. So these are the measures for this any image steganography techniques. One thing to understand for this diagram, like these three, these parameters are quite complementary to each other in the sense quite opposite to each other. I mean to say, when you want to increase the capacity of a technique, then ultimately you have to sacrifice. It will sacrifice the output image quality, the imperceptibility, or the this robustness, and it's the vice versa for all other parameters also. So let us start this the first technique, LSB technique. If you see this diagram, the cover image is a kind of medical image, and a block of pixels has been taken, original medical image pixels, which is actually a block consisting of 16 pixels. Now these pixels are again converted into its binary form. You can see the right hand side picture, okay, right hand side matrix, I would say, binary matrix. These are nothing but the 8-bit binary values for these pixels. The last bits are colored in red, which means these are the least significant bits. Sorry. These are the least significant bits, or I would say LSB bits. And this technique name is least significant bit substitution technique. And in this, we are going to replace the least significant bits with the secret bits. We have secret bits or secret messages or confidential information is given here, 11100 binary informations. We have converted into binary. Now this will be replaced by the least significant bits, right? So we'll just directly put these bits in the last bit of these binary pixels, I would say, right? So then once again, after replacement of these secret bits in the binary bits of the medical image, we'll reconstitute the binary bits for the individual pixels to decimal bits. Okay. At the end, I have highlighted the pixels which has altered or changed after hiding the secret bits. Now, this new pixel or this new matrix is your part of the stego image. Okay, corresponds to this cover image big block, right? So this is quite simple and early use of this famous least significant bit substitution technique. Now, this is what we do embedding, and the extraction I haven't explained, and it is quite opposite to this embedding process. I mean to say this, the receiver will be receiving the stegomedical image. From there, it will extract a four-course 4 block, and then it will find out the binary of these bits in a pixels, and then the last bit it will take, right? Then it will get the secret information or secret message or secret bits. This is called reversible, I mean irreversible. All right. So therefore, LSB is usually, mostly famous for irreversible technique where we just retrieve the embedded information or any kind of medical information, right? So, but we are not getting the original pixel back. Okay, in this case, it's quite interesting to see. If you get it, then it is called as reversible one. Okay. Now, one technique, another technique for this steganography, popular technique, I would say like LSB matching, least significant bit matching technique. Okay, you can see here, like I have just explained an example for this technique. Okay, like suppose we have two original pixels, 32 and 128, O1 and O2, and in this technique, what happens? Each pixel hides one bit, and initially we will consider at a time two pixels and two secret bits. Consider two medical bits or two any kind of bits are B1 and B2 whose values are 1 and 0. You can take any value, no such restriction. The whole algorithm is depends upon this equation. Right hand side it is given. Okay. Now you see whatever the equation is given in the right hand side, the flow diagram I have made in this picture. Okay, if you see what does this diagram says that uh, this is process of embedding actually. Okay, now embedding as well as extraction. So what is happening here is first it checks is the first LSB is 1. Okay, the first bit of the first pixel, that is 32 O1, is LSB of O1, that is 32, is 1. If yes, LSB of 32 is not 1. Okay, so it will go to the no side, right? If yes means it will go to the right side. If no, we will check one more condition involving the second bit also, second pixel also, O2, is LSB of 32 minus 1. LSB of O1 minus 1 divided by 2, the base value, plus 128, the O2 value. You can see that LSB of 32 minus 1 is 31 by 2 is 15 point something, and the base value is 15. 15 plus 120 is 143. Okay, is 143 is equivalent to 0? No. So again it will go to the right side. If it goes to the right side, if you see the equation, the first two condition fails. Then the stego pixel value O1 star, O2 star. It is stego pixel for the corresponding O1 and O2. The O1 star will be O1 plus 1, that is 32 plus 1, it is 33. And O2 star will be 128 as it is. Now this is your stegopixel. Since two binary bits we are hiding, we can have four possible conditions. And for each conditions, you see at the intermediate there are four possible conditions here. Okay. One of the condition will satisfy at any point of time. If you see here, the stegopixels are 33 and 128. And from here, this will be sent to the receiving end. And from here, how the receiver will find out the hidden information? What is the hidden information? B1 and B2, 1 and 0. Okay. How does it will find 1 and 0? Just it will find the LSB of the first stegopixel. That is 33's LSB is 1. So we got it B1. And then it will apply another equation that it is also mentioned in the right side. Okay. The received O1 pixel, O1 stegopixel divided by 2, its base value, plus O2 star. So 33 by 2 is nothing but 16 point something. Its base value will be 16 plus 128, 144. Its LSB is 0. So the receiver can extract 1 and 0 from these two stegopixels. This is how this algorithm works. Next. One of the important and famous technique in data hiding in steganography is pixel value differencing data hiding technique. In this data hiding technique, what it does is it takes two pixels from the image as a block. Okay. Now consider we assumed the two pixels value is O1 and O2 and the values are 98 and 116. Then we will find the difference value between these two pixels. Yes, yeah, it is 98 minus 116. So we'll take the mode value. This is 18. Okay, minus 18, but it will be converted to plus. Okay, mode value is taken. So magnitude is 18. So this is the difference value. Now this difference value will be corresponding to one of the predefined range table. The range table having 6 ranges ranging from 0 to 255. You may ask why 0? Because the pixel value's lowest value is 0 for an image, and 255 is highest for any image or any object, digital object, pixel value. Now there are 6 ranges corresponding for this difference values, and the difference value will fall into one of the range. Considering here 18 is falling in the third range. In every range we have a lower range and in an upper range. The 18 belongs to the range of 16 and 31, where its lower value is 16, lower range is 16 and upper bound range is 31. Using these two lower and upper bound, we will identify how many amount of information to be embedded in these two original pixels. All right. So here we have 16 is the lower bit bound and 31 is the upper bound. And the equation to find out the number of amount of embedding bits is nothing but logarithm log base 2, the upper bound 31 minus 16 plus 1. Okay, is nothing but 4. So 4 bits, 4 number of bits will be embedded in these two original pixels O1 and O2. Assume that some 4 bits is 0, 1, 1, 1. Anything it could be. I have actually considered it as 0, 1, 1. Could be anything. And its decimal value is 7. That's fine. 0, 1, 1 is 7. Now what the next step is to find a new difference value, FV prime. You see, the FV prime is nothing but the decimal value 7 plus the lower range 16, that is 20. Now it becomes altogether is 23. So the new difference value is 23. Then what we will be doing, we will be finding the difference between FB and FB prime, which is 23 minus 18 is 5. All right. So this is the difference between new and old difference values. Okay. Now, the given equation for finding the stegopixels from the given original pixels and having the difference value D is given here. O1 star comma O2 star would be O1 plus D by 2's floor. That means O1 star would be this one, provided if O1 is greater than O2 and FB prime is greater than F. So one of the condition among these 4 will be hold. In this case, you may see the second case is holding, the marked green color mark. Since O1 is less than O2 and FB prime is 23 is greater than FB 18, right? Therefore, O1 star, the stegopixel O1 star will be O1 minus D by 2's floor. O1 is nothing but 98. 98 minus D is how much? 5. 5 by 2 is how much? 2 point something 5. Its floor is 2. So 98 minus 2 is 96. O1 star is 96. Similarly, O2 star will be O2 plus, O2 is 116 plus D is nothing but 5 by 2, D is 5 divided by 2 and its ceiling value, that is 3. So 116 plus 3 is equal to 119. These two are the stego image or camouflage image blocks, modified pixels. This will be received to the receiver by the receiver. Here, the difference between these two will be calculated at the receiving end to find out the secret embedding bit 0111. The opposite process we will be doing, the extraction process. Here, 96 minus 119 is how much? 23. This will be again scanned through the given range table, same range table. Now this is coming in the third range. Now that means we have to extract again same equation, log 2 31 minus 16 plus 1. 31 is the upper bound of 16 is the lower bound, plus 1 is nothing but total is 4. 4 bits we have to extract. From where? That we will find from this, you see, this left side end of your screen. How we will find? If we star value, that is 23, minus this 23 belongs to which range? Its lower bound is 16. 23 minus lower bound 16 is 7. You see, 7 is the decimal value for the embedding bits. Its 4 bits are 0, 1, 1, 1. Understood? This is how the pixel value differencing method works. This method was the first proposed work in pixel value differencing technique. After that, thousands of modified PVD techniques have been proposed. Right? This method having lot of issues, problems, drawbacks, most of the researchers have found. One of the problem is PDH analysis, pixel difference histogram analysis. What happens? PDH analysis is used to find out the presence of secret information in PVD based techniques. This is particularly known as steganalysis technique. Steganography means hiding the data. Steganalysis means finding the presence of data. So, PDH analysis, pixel difference histogram analysis, we can apply to any technique, any steganographic technique. But largely or mostly, this is applied to PVD techniques, as PVD techniques are more vulnerable to PDH analysis compared to any other LSB or modulus function or edge-based techniques, any other techniques. They are more vulnerable. So what is this PDH analysis? If you see this PDH analysis, here we will find the difference between the original and well as this obtained stego image using the histogram. This is implemented as follows. At first, we'll create blocks of 2 successive pixels each. Right. Let Vi be the fluctuation between 2 successive pixels in each block, and Vi will be in the range of 0 to 255, no doubt. Okay. Then we will calculate the frequency of each Vi. Okay. And then we will plot a graph with the frequency of Vi in the x-axis sorry, y-axis, and the difference of pixel in the x-axis. Okay. So 2 pixels difference will be plotted in the x-axis, and the y-axis will be showing the frequency of these occurrences. Okay. All right. Next, if we draw the plot for both cover and original images, we would be seeing these two kind of pictures, possible two kind of pixels. Okay, I mean, one you can see there are two signals or two images here. One is original one, another one is stego image or camouflage image. In the first graph, you see both the images are overlapped with each other. It means the technique do not find any information from the stego image. But you can see the second graph here, the two images are apart from each other. It is in zigzag shape. And there is nowhere merging happens or merge with each other. It means that there is some information has been embedded inside the image. You see, particularly in case of the original image, it will be a smooth curve, whereas for the stego image, it will be a curved curve. There will be a zigzag images in the zigzag images for the stego image, right? But if you see the pink color image, it's an original Lena image, which is quite smooth, and this is true for all the cover images. So, by discussing all these techniques, if you come up to a conclusion to find out the challenges and the objectives of data hiding techniques, you may find that the objective of any data hiding technique is to improve the output image quality or stego image quality, that we say imperceptibility. Improve the capacity, so considerable amount of data can be embedded inside the image. Improve the robustness, so that it can resist different types of attacks. Now, with the advent of ML and DL based algorithms like CNN, ANN, RNN, the entire embedding and extraction process has been automated, because they can capture the convoluted dependencies among the pixels. They analyze and identified the dependencies among the pixels. Therefore, these ML-based technography, steganalisis techniques significantly challenges the heuristic or conventional image steganography techniques. Because the conventional image steganography techniques are well handcrafted, but they are a heuristic in the sense certain level of expertise is required to understand where and how exactly to embed the secret information. In case of the old conventional image steganography techniques, handcrafted techniques. However, conversely, with the minimum effort, deep learning based techniques using CNN can accomplish this work with minimal effort. The only thing with CNN is to have to decide the structure of the encoder and decoder. The ANN can effectively identify the optimal embedding location in the image. Therefore, in near future, it is expected that the fight between steganography and steganalysis is going to be the fight between the neural networks. Also, it is expected that the trained AI models can perform the embedding and extraction independently when they are trained and supplied with the necessary features or inputs. So with this, it will reduce the human intervention in performing the embedding extraction to a greater extent in coming future. Therefore, XAML-based techniques are promising to pay great attention to achieve many wonders in the steganography as well as steganalysis domain. So one of the machine learning based technique is optimal embedding location finder model. This is particularly used to protect the embedding process from steganalysis or any form of distortion in image must be minimized after the data is being hidden. What happens? The cover and stegomage must be approximately or visually or statistically identical. The selected areas and the embedding methods are the primary factors that affects the distortion. Most traditional steganographic methods embeds the message in an image by ignoring its statistical significance, convoluted features, spatial features inside the image. However, the identification of ideal embedding location is critically decided by the block's message homogeneity and other textural features. A location having least image distortion is considered to be the optimal one. In general, steganographers can embed the medical information in the edge regions compared to smooth regions of an image. So, researchers have used various edge detection techniques such as Sobiel, fuzzy, Previt, canny. However, all these detectors fails to find more edge regions from the image. These detection approaches requires complex manual tuning and pre-processing. Some authors have recently utilized CNN with deep learning supervision-based edge calculator. They can retain more edge pixel compared to your traditional edge detection approaches such as Sobiel, Previt, canny, and fuzzy detectors. So there are a few facts related to the image. If you take an image of size 512 by 512, grayscale image, it consists of 262 144 pixels. Every pixel has different intensity values. Therefore, the placement of the individual pixel in image is quite essential. Manually understanding the correlation of the pixel is quite impractical. Therefore, deep learning techniques learns the features from the image independently without human intervention. So, if you see the CNN is a network architecture that has successfully proven its ability to find the patterns from images, correlation between pixels, classes, etc. Also, the CNN has efficiently solved complex image classification problems by identifying significant and distinctive features from the without manual interference. As we know, CNN extracts the features through multiple convolution and sampling layers. This is one of the diagram for CNN. Convolution, activation, cloning, flattening, fully connected layers. Right. So this is what the whole thing about today's talk. Just to summarize at the end, the CNN about CNNs. To the CNN consists of layers like convolution, ReLU, pooling, fully connected layers. The first layer of the CNN is convolution layer. This layer contains series of filters, kernels. Usually the kernel size is smaller than the input image size, and the kernel convolves with the image to produce feature map. Next, the ReLU function works in the hidden layer to control all input neurons. The negative input stops the neurons from activation. Some popular activation functions are sigmoid and Tana. So this process is known as down sampling. We have also max pooling and average pooling methods are there. The pooling layers return highly essential features. Finally, the flattened matrix is fed to the fully connected layer to identify or classify the objects. So if you see, this is the CNN once again, a block of 7 cross 5 pixels is taken. We'll apply CNN to a particular block. Then we'll go to the summation and then activation, then output. You can see a block, convolution, ReLU, pooling, layers. And if you see one example, considering this 7 cross 5 image, and these are the pixels, and we have a filter right side. We can have both loop as well as vertical line filters. The filters will convolve on top of the image. The first convolution, okay. Now we will find the average convoluted value and put a new matrix. And finally, this process will be convolving and take right shift of loop filter from one cell of the block image to another. And then we'll multiply the values and add them and we'll find the average. The whole process will be continued, sliding over one stride of one of every iteration, and we'll find out the new feature map with 5 cross 3 new structure. So this is all about this convolution, then pooling as we discussed. So this is all about my presentation. I now request this organizing team to handle. Thank you very much for this wonderful opportunity. Any doubt, please, we can discuss.
Thank you, sir, for the very informative session.
Thank
So
you.
now I would like to ask the participants if you have any doubts regarding the lecture, you can directly ask to the sir. Any question? So right now I don't think any question is there from the participant side. So if you have any question regarding the lecture afterwards, also we can share the mail of Sahu sir, and then we can directly ask the question via
Yes, sure.
mail
I
also.
would be glad. I would be glad to have a wonderful discussion extending on this topic. This is my PhD area. It's technography, watermarking, and I would be glad to extend this work. Presently, I have three co-PhD full-time scholars. Okay, and I would be glad to work and associate anyone who really wishes to contribute to this domain. Really appreciate. And this is my Google Scholar link. I hope it is visible, and I would be glad to have this association, collaboration, on funding or paper writing. Okay, everything related to research and consultancy.
So that has already shared his Google Scholar mail ID, everything. So anyone who is related to this field can contact with sir directly. And thank you again, sir, for this joining with us and have a very informative session.
Thank
And
you. Thank you very much.
in the future also, if we can collaborate with us in some other topic, then we'll also very glad. And
Always, my pleasure it is.
okay,
Anything
sir.
related to machine learning, cyber securities, particularly watermarking, steganography, any speech, anything research works, I would be glad to present. Thank you.
Okay, sir. Thank you for joining, sir. So with this, we conclude this session. Thank you.